Hello, everybody. I guess you can see the screen.
Yes, we can see.
Great.
Yes.
So it is our introductory slide on structural integrity and life of hip implants. I will get some help from my student, PhD student, Alexa Milovanovic, who will take over later on when some case studies will be on the agenda. You will see in this presentation that we are dealing with metallic materials. So previous lecture was excellent introduction in general and of course focused on polymers. Now you will get another view of biomaterials from the metallic materials point of view practically. And why is that? Well, we are dealing here with orthopedic application. We are dealing with hip implants. And hip is a typical bone that carries a load. And once we have this situation, which is both static and dynamic, we practically have to turn to, I would say, good old metallic alloys, unless we use some very specific materials like composites. But anyhow, what I will show you today with help of Alexa is a possible choice of three materials which are used for hip implants, and those are stainless steels, cobalt chromium, or sometimes called cobalt-based alloys, and titanium alloys. Historically speaking, stainless steels and cobalt-based alloys were the first to be introduced. But then again, titanium alloys, which are the latest, are nowadays also the most popular and dominant. Now, there is, of course, a reason for that. And this is, I would call, optimal combination of properties, and especially the so-called shielding effect is the least with new, especially with new titanium alloys. This is due to significantly smaller modulus of elasticity, and also titanium alloys have significantly less density than both stainless steel and cobalt chromium alloys. Anyhow, for all three of them, these are three different types of materials. There are many versions when we come to application. So for cobalt-based alloys, a couple of basic characteristics are listed here. Of course, some of them are related to corrosion and corrosion resistance. This is extremely important. Some of them are related to wear, because it is also quite important characteristic of material. I may even now say, if we try to find some backwards, something that would hold us from using titanium and titanium alloys, this is a bit higher wear. That means a lower wear resistance. So implants made of titanium and titanium alloys tend to get some debris from time to time, and that's really bad news for that type of alloys. Anyhow, you can see here a list of basic properties. All three categories, of course, have good mechanical properties. So these are just small subtle differences that allows us to differentiate between them and to choose whichever is optimal and best for our application. So more concretely, you can see here a list of mechanical properties, and you can see that modulus of elasticity for bone is in the range of 15 to 40 gigapascals, whereas chromium, cobalt, molybdenum alloy, one of these cobalt-based alloys, it's more than 200. Stainless steel is close to 200, and then commercially pure titanium is 110. Some popular titanium alloy like this 6 aluminum 4V is 116, but newly developed alloys like 13 niobium, 13 zirconium, they are just 80, which is definitely closest to the bone. So once again, this shielding effect, which is very important, is in favor of using newly developed titanium alloys. Now for the strength.
Alexander,
Yes,
Alexander,
yes,
sorry,
Vladimir.
you could consider having the full screen for your slides, because we can also see the suggest row of your small slides.
Okay, okay. There is one drawback in that, but not a big deal.
If it is planned, then it's fine. I have no problem.
I can't show exactly what I want to point out, but I think it would work also good.
Sorry, sorry.
We'll
I
see.
didn't want to interfere.
Let's try this way. Okay.
Yeah, because now it's much easier to read. Sorry.
Okay. Okay. We'll try this way now. So we will focus our attention to titanium alloys today. As others, it's very resistant to corrosion, probably even better than others. It's certainly better than stainless steel. And several different types of titanium alloys are listed here. Just pay attention, those who like material science, they should pay attention to alpha and beta modifications. This is multi-phase. Alloy beta is stable at a certain temperature range. It is above 882, and below 882 it is alpha, which is hexagonal. And so there are of course then different options and possibilities how to heat treat these alloys and make most of it, as you certainly remember from your engineering material courses or material science courses. So once we covered materials a bit, and once we maybe learned that nowadays titanium alloys are the most popular, we can focus our attention more to hip replacement itself. But allow me to go back. I forgot to emphasize the last two rows in this table. Actually, it's out of the table. Some basic data about impact and fracture toughness for these three types of alloys. You can see for impact toughness that stainless steel and cobalt-based alloys are superior to titanium alloy. Nevertheless, impact toughness of titanium alloy is good enough. Then for the fracture toughness, we can also see superior behavior of stainless steel and good enough behavior of cobalt chromium alloy, and titanium alloys are once again with the lowest toughness. Sorry, I just noticed that it's wrongly written. Fracture toughness is the first row, impact toughness is the second one. Sorry for that. We will correct this. But the main message is that titanium alloys are a bit brittle, not as tough as other two. Anyhow, in applications, that's not that much important. They fail from time to time, but not that often. So we are now back to this hip replacement issue. So you can see the normal hip and then you can see how it looks like after replacement. It's a bit scary, but well, this is how it is. And our task from point of view of engineers, from point of view of people who are dealing with fracture mechanics, our task is to ensure prosthesis integrity and of course life later on when we deal with fatigue. So fatigue, fracture and wear are actually major problems. And this is why we focus mostly on fatigue. You will see later on. Of course, there will be some classical design issues and stress state calculation and evaluation. But don't forget also that wear makes problems very often. You can see here that so-called predictive and design tools can enables us to prevent failure in vivo, and that means, among others, the most important causes of that would be aggressive body environment and large cycle loads. Other mechanisms are not very important at this point, but just keep them in mind. They are listed as well. And a couple of slides regarding research methodology. We surely start from design aspects. You can see in this scheme about the forces that are acting and how they are changing in a cycle of walking. And you can also see that intensity very much depends on type of walking. So those who are jogging, they have several times more intensive load than those that just keep calm and slow walk. So it is obvious that we have to face very different loading intensities and even different loading types. It is very individual. To test an implant, we may use ISO standard. You can see in this sketch how it should be performed, and you can see one simple solid model of testing arrangement. So you have to adapt your machine for this specific type of geometry. And then again, there is another very important tool that we can use for strain measurement and then stress analysis. This is nowadays very popular digital image correlation. You can see this scheme, how it works. There are two cameras, and interference between them enables us for very precise measurement. So this is about what I intended to tell you in a kind of a general explanation what this lecture is about. And now I give a screen, not a floor, to my colleague Alexa, who will replace me.
Yes, hello. I'll continue from this slide. So the human hip joint consists of two surfaces, an acetabulum, which is a concave surface of human pelvis, and femur head. So the hip joint is a ball and socket type of joint, as you see on the picture down. Both of the surfaces of the joint are covered and protected with cartilage, a very resilient and smooth elastic tissue. So the problem with the dysfunctional hip is when the cartilage starts.
You are muted. Alexander, you have switched off your microphone.
Sorry,
Nice.
it was self-closure. I don't have idea why it happened. Okay.
Okay, now
Touch
you're...
anything. Okay, may I continue? You hear me? You see the slide?
Yes, now it's okay.
Okay, thank you. Well, in case of a surgical operation for hip implant, will include large bone and cartilage removal, which includes a replacement of a joint. So, in that replacement, surgeons may make partial restorations, as you see on the picture to the left, where there you have only a plate and few screws to attach both sides of the femur bone where the a breakage was present. And then you have a total hip replacement where you replace a complete joint. So you have a stem component which is placed in the medullary canal of femur bone. On that stem, you have a neck holding a femoral head. That is the first surface of the joint. And on the head, you have neighboring to it a plastic liner. It is a UHWPE based polymer cup. And above it, you have a metal cup which is placed and screwed, fixed in acetabulum bone of human pelvis. So then, as we see here on this slide, total hip replacements, when you replace a complete joint, they can be non-modular design, which is a case in the picture to the left, when the whole joint is in one part. And then you have a modular design consisting of a few components. Stem on which you have a neck, then above it head, and as I mentioned, a polymer cup and metal back. So implant head is nowadays made from ceramic materials, usually alumina and zirconia. Stem is a bearing element. It is present on the picture below. So as a bearing element, it is made of metallic materials. Previously, the most usual material was cobalt chrome based alloys. Nowadays, they are mostly titanium based alloys because of their good combination of mechanical properties and above all, excellent biocompatibility. Hip implants may be cemented and cementless. They can be placed in the bone with a PMMA coating. That's usually made for older persons. For the PMMA to be sort of a glue between bone and metallic material. Cementless method. In cementless method, hip implants have a porous coating in which a healthy bone ingrows and makes a tight constraint between prosthesis and the bone. So as all things in life, implants have limited lifespan, and of great concern is the problem of their failure. The failure might come as implant loosening of the metal component from the bone, eventual dislocation, and wear of material if there is any abrasion between the implant head and the cup placed above it. The thing with wear is that by using ceramic-based heads, the wear is not the thing we should concern that much as some other issues, as fatigue, for example. So due to dynamic loading of everyday activity, we make dynamic loading on regular hip joint. So the most usual failure of this type of implant is due to fatigue. So any types of defects in the structure, any inclusions and microcracks may also influence the stress states, mainly the residual stress in the implant, but they're not usually taken into consideration because most of today's implants are made by powder metal techniques with hot isostatic pressed, hot isostatically pressing the alloy. So the inclusions and that type of volume defects are not usually taken into consideration when we are experimentally and numerically testing these implants. So the main concern with the hip implant are the locations with the highest stress concentration. That is where we usually expect the first cracks to come. And in the simulation, we place the cracks on those locations on the implant. So the locations of cracking of first cracks are usually in the neck area. On this here implant, it's not the case because the lowest cross section was somewhere in the stem, and this is and on this here picture you see where on which location the implant failed. So when making a experimental setup and doing numerical simulations, you have to consider which type of loads you can apply. So in this here table, you see the forces exerted on a hip joint during each everyday activity. So during stumbling, you have the highest force exerted on an implant. In this application, scientists are using load expressed in body weight. So in the case of stumbling, where you see on the lowest row, the stumbling makes 8.7 times the body weight of a patient. So you just multiply it with his body weight and gravity constant, and that's the force you have for that case on that implant. So our previous research shows that the value for stumbling is fairly convenient to see just the stress states on the implant, just to see the locations of maximal stress concentration. On the pictures below, you see to the left the location of maximum stress. None of these loads from the previous table can cause static failure of an implant. So this is just to see in a linear elastic analysis the stress states of an implant. So the locations of the highest stress concentration show the most probable place for crack initiation. And as I mentioned before, the most probable place in the neck is in the neck area. On the pictures below, that is the case with that type of implant. Here on the pictures, you see two different numerical models. They both have a collar. This platform beneath the implant neck is that collar which faces the upper side of human femur bone. So if we see the neck area as a beam, in a beam when it is loaded on one far end, in the structure, you will have tension and compression zones. So the main idea is that the maximum stress concentration would be on the other side, on the side of compressions. If a crack starts to develop on the tension side, we'll have a mode 1 fracture, the most inconvenient one, and the crack which will grow in the fastest manner. So with our studies of hip implant tests, it includes experimental and numerical type of tests. In experimental tests, we include acquisition of mechanical properties of metallic biomaterials on standard tensile testing machines. So that is when you need to acquire basic data from the metallic alloy you are using for the hip implant. Then the next step is the acquisition of Paris law parameters, CNM in particular, on which you attain on high frequency resonant testing machine. And the last but not least is the simulation of real implant stem loading, when you actually assess fracture in a experimental testing. Then numerical tests consider static numerical analysis for determining of stress concentration locations. Where will you place the crack? And then for that purpose, the next step is an XPAM analysis, where you consider crack type defects and simulate crack growth. Now, the acquisition of mechanical properties is done on a standard tensile testing machine. In our previous research, we used a microspecimens defined by ISO 6892-1 standard. The results acquired include yield stress, ultimate tensile stress, the elastic modulus, and so on. Then just to consider the next step, which is fatigue. For fatigue testing, we are aware of a Paris law, which holds CNM constants for describing material behavior. The Paris law shows the behavior of material in fatigue in the second region. Of course, we have some other equations which include second and third, and first and the second region. The region of and an Asgrove equation, which is the last step, is the equation which includes all three regions of testing fatigue. So what we are using is the Paris law in most of our cases. Then to assess parameters of fatigue, we use a CT type specimen according to standard ASTM E833. To point out that all the specimens considered must meet the plane strain condition in order to the testing to be valid, which with CT specimens on a high frequency resonant testing machine, we acquire fracture toughness values. In one previous research we did, we tested 3 samples and used the average value for fracture toughness and used it for the next step. So the next 3-point bending specimens were used to acquire crack growth rate, dA over dN, and a fatigue threshold. From a 3-point bending tests in that experiment, we attained a regular fatigue graph with dA over dN independence of delta K values. And this is how we get material constants C and M. So we see that the exponent M is always between 2 and 4, so the attained values are valid. Then the last is the fatigue standard, ISO 7206-4, and there are some other standards, 6 and P58. This is a complete fatigue testing of hip implant. So the hip implant is placed in a cement mantle in which a lower part, which is regularly in bone, is fixed. and the load is applied from above on a high resonant testing machine. On the picture in the middle, up, you see that you measure some angles of force application. So in the real case, looking at the right picture, a hip implant is placed under a minor angle between two axes. So in one axis, it is displaced for 9 degrees inflection and displaced by 10 degrees in adduction. So placing the implant in the right manner in the cement mantle, you can test it on a high frequency resonant testing machine, and also you can include a fluid test medium to test the temperature and just to simulate the regular hip implant environment in human body. So next are the numerical, I'll focus on numerical simulations. So the first thing you need to have, and which is not that very simple, is attaining numerical models. So the hip implants contain complex geometries and require demanding CAD modeling in regular CAD packages. The additional assistance is by using the 3D scanners. So you place a implant on a turntable of a 3D scanner. The one thing above is the scanning head. It uses 2 cameras and lightens the implant with an UV light and captures and records the sections. With recording sections, then you mesh all the sections together, making just a pattern to make a CAD model above it. As you see here, we had videos in this here slides. I can't open them. So what we make with the mesh is a point cloud on base of which we create a CAD model. So on the next slide is a standard deviation showing that by creating a CAD model, we had not more than 1 millimeter dimensional deviation in both directions. So there were no so the maximum deviations here were just not over 1 millimeter, so the attained CAD model is appropriate for the analysis. Then using that model, we convert it to step file and use it for a static numerical analysis, just to determine the stress concentration locations for the next step by using XFAM for crack growth simulation, where we place the crack in the locations of maximum stress concentration. So for the FAM, we use Abacus and ANSYS. In most cases, we use Abacus for static analysis and ANSYS for XFAM because of its better packages containing the ANSYS FAM software. Then you see on the picture to the left how in the numerical analysis we acquired the loading. So we use the coupling constraint from a reference point. You place a force from above directly applied on a hip head, and the load travels to the stem from where we will look the stress states. So for the FAM analysis, we used linear elasticity as a for material. So for that type of analysis, we only need Young's modulus and Poisson coefficient for a particular material. On the slide, on the table below, you see how many total number of nodes and elements and which type of element we used for the analysis. Then in the numerical tests, any type of initial defects are difficult to be performed in a FEM software. So the XFEM method is developed in order to calculate the simulation easier. It uses enhancement functions for all forms of discontinuity behavior, such as crack displacements. So compared to the classic FEM, XFEM provides significant improvements in field of numerical modeling of crack growth. In traditional FEM simulation, the existence of crack is modeled in such a way that crack must follow the edge of elements. Contrary to that, the XFEM does not have to follow the edge of the elements. It will so it allows the greater flexibility during modeling. So the nodes in XFEM analysis have more degrees of freedom, and the whole method is based on enriching the model of finite elements with additional degrees, which are related to the nodes of elements where the crack cuts. In this way, the discontinuity is introduced into the numerical model without changing the discretization of the model. So with only one meshing, XFEM performs a simulation. So numerical models are made in order to analyze material behavior of implant during load in an ideal case when there is a crack in material. So many type of factors that influence the integrity, such as state of bone, effect of corrosion, and how much there is biocompatibility in the alloy, is not possible to simulate all the effects, and since they depend just on individual cases. When performing a numerical analysis, it is necessary to use approximations in order to obtain required results. In all of our analysis, we assume that the material is homogeneous, isotropic, and linear elastic solid body. So models need to have appropriate set of boundary conditions to simulate the behavior of implant in accordance with the bone. Whether if you fix the contact between the implant and the bone, or may you consider additional degrees of freedom. The loads are applied in the defined direction showed on the picture below from a reference point directly connected to implant head. Then the fatigue crack growth simulation, with using XFEM. On the picture to the left, you see how we applied the load. And on the picture to the right, with this particular disc in brown color, you just cut the geometry and place a crack on that place where you had maximal stress concentration. Here you see the meshing and how many nodes and elements we used. The finer mesh is usually applied in the vicinity of the crack to acquire better results. Then to point out again the type of loads you can make. So you can make different numerical analysis just by applying different intensity of the load. So for acquiring the maximum stress concentration, it is convenient to use tumbling just to see zones of stress concentration better. And in fatigue analysis, you'll try to simulate the real case in everyday activity. So usually we are taking the values from the first 3 rows, the type of walking in a slow, normal, and fast manner. It is not that usual to jog every day during the whole day. So for the analysis, we just use the walking cycle. Here we had a video of crack path. So I'll just explain it to you. From the crack where the mesh is finer, it just propagates to the almost to the end of the hip neck, and at the final step it collapses and the simulation was finished. Here you see the stress states in one particular step of fatigue crack propagation simulation. So you see that the maximum stress states are on the far ends of the crack, where it propagates the most. On the picture to the right, you see the change of K1 values along the crack front. As you see, the first and final dots show the stress states on the far ends of the crack. Abacus software creates steps during the fatigue crack growth simulation. So it will generate about 100 steps. Each step includes how many cycles it was performed, the simulation was performed in each step, and what you attain finally are the results of K1, K2, K3, and K effective for all generated steps. The highest value and the K1 is in few orders of value greater than K2 and K3 and is close to K effective. So the K1 value depicting the mode 1 type of fracture is relevant for the analysis. Then as results, we have 2 graphs. Usually we consider 2 graphs as a result. The first one to the left is the K1 value depending upon crack length, and on the picture to the right, you have a crack length depending upon the number of cycles. So based on these 2 graphs, you see when an unstable crack growth begins from a standpoint of crack length and number of cycles. In particular case, you see on the picture to the left that after 19 millimeters of crack length, unstable crack growth begins, and it is very close to final failure. And on the picture to the left, it is to the right, you see the same case but expressed in number of cycles, which is somewhere in between 7 million and 8 million cycles. So for the conclusion, assessment of structural integrity of hip implants includes a combination of experimental and numerical methods, where we can get a good estimate on structural life of implant component. The structural life of implant depends upon chosen amplitude of loading from the table before, and of course its frequency and level of approximation. Have you considered corrosion, biocompatibility, and that's a type of parameters. So the initial crack, for numerical analysis, the initial crack is placed at the position where fatigue cracks will most probably start to grow, and that is the location of maximal stress concentration if situation is ideal. The crack will begin to propagate on the location of maximum stress concentration. Crack grows in the X-time analysis until it reaches a critical length, whereupon a critical condition occurs in terms of uncontrolled and accelerated crack growth. If it is assumed that the crack is unstable when due to influence of the external load, it achieves critical condition, and for that case, it can be assumed that there is a phase and unstable crack growth on the numerical model of an implant. So for the crack growth, we use XFAM simulation, which is proven to be a very effective tool for numerical modeling of cracks, crack type defects, because we only use one type of mesh, and that is where the FAM simulation lacks. It will have to generate mesh for each individual step. So by using the XFAM, we can generate the fatigue crack growth, and in comparison with the experimental results, we can compare these two and conclude the after how many cycles and after which crack length the unstable crack propagation to final failure will come. Thank you. This is all for our presentation.